Hello everyone and welcome back to another video. Today I show on register number URK 20CS3026. I'm going to explain to you experiment number 5 of Introduction to Data Science Lab. So today we will be doing statistical inference. So statistical inference is basically like inferring the properties about a certain data set, that is maybe a population for instance, and testing hypotheses and deriving estimates about the population. So there may be many assumptions about the data that we have, and but like and through hypothesis testing we get to know like at what confidence interval or at by deriving estimates we get to find out that at what like are the estimates going to prove that like our assumptions are right or wrong. So here we are assuming that the observed data is taken from a larger population, and sample mean is like a arithmetic mean of the uh, sample values of the population. And here we have confidence interval in statistics, which refers to the like test statistics, and like it measures the statistical relation or association between two continuous variables. Then we have Pearson's correlation coefficient. Then we have Spearman's correlation coefficient. Covariance matrix, which is a symmetric matrix that shows covariances of all the variables. And finally, we have hypothesis testing, which is a form of statistical inference in which we will be able to draw conclusions about a population parameter or a population's probability distribution. So the first part of this is like importing all the dependencies, that is pandas, numpy, matplotlib, and sci-fi stats. And after that, the first question is to find the sample mean for age column with n like size 400 and sample size 500, and compare the population mean. So firstly we will be taking S1 is the size of the first population to be 400, and S2 is the size of the second population, which is 500. And in these two, the first sample, first sample population, we'll be taking it out to be, we'll be taking 400 random samples, that is random rows from the data frame in the column age, because we are going to calculate the like sample mean for age. So we'll be taking 400 random samples from this, and similarly S2 will be taking 500 random samples. Then we find the mean using the predefined function mean, and similarly for S2 also we find the mean using the predefined function mean. And finally we find the population mean, which is for the entire column of age that is there, all the values mean it finds out. And then we display all the three, and as you can see there is a slight variation in all the three, because like this is taken for 400, this is taken for 500, and a random 500, random 400, and here this is for the entire population. So here we have like calculate the sample mean for kilometers column with n is equal to 1000 and observe. So here we have taken the sample size to be 1000, and then we gather the sample of like size 1000 from the kilometers column, that is 1000 samples of kilometer, like 1000 rows of the kilometer column in our first sample chosen randomly, and then we find the mean and we display the mean. Then we find the population mean for kilometer column. Population mean will be just taking the kilometers column, finding the mean of that and displaying it. Then other than that, here we have calculate the confidence interval for the sample mean for age column of n is equal to 500 and a confidence level of 95%. So observe whether the population lies in the confidence interval. So what we do over here is we first take a sample population size 500, then we find the population mean just by taking the columns mean, age columns mean. Then we will be taking randomly size of 500, a random population, like random rows of like random 500 rows to create a sample population 1 and find its mean. Then we will be finding this sample's standard deviation over here and showing it. Then here it's given that like to take a confidence level of 95% and calculate the confidence interval. So over here we have taken a confidence level of 95%, and here we find alpha, which is like 100% minus the confidence level. So that will be equal to like 0.05 in this case, divided by 2, which is 0.025, and then we find z-score. Z-score is generally a huge formula in manual calculations, but when we do it on a machine, we have a predefined function in stats from sci-fi in which there is a normalization ppf function, in which if we give 1 minus alpha, that is the confidence interval value by into 2, if we give that value, in that case we will be ending up with the z-score, and we print the z-score with rounding off the value to 2, because z-score, the value was really like huge, so we wanted just 2 decimals. And then we find error. Error is found, basically we have z-score and we multiply that z-score with standard deviation divided by the square root of the sample size. So when we find that, then we can find lower limit of the confidence interval, which is the sample mean minus the error, and the higher limit of the confidence interval, which is the sample mean plus the error. And then we can display the confidence intervals. After that, we can change the confidence interval to 99% and do the same. And as you can see, they have slightly differed because here we have changed it, the confidence level to 99%, and so the interval again drops. And after that, we can calculate the confidence interval for 20 trials. So here we are finding the, like here we are just making 2 empty arrays and defining size of the population to be 500. After that, we take the confidence level 95, find alpha, find the z-score, and after that we run 20 trials using this for loop. Each of these trials we find the sample mean for a random 500 samples of age from the data set, and then similarly we append that to the sample mean list, and then we have standard deviation which we find, we append that. Then using that we find the error, and then we find the confidence interval. Confidence interval, again as I said, is sample mean minus error and sample mean plus error. That is the lower limit and the upper limit. Here we round it off to the nearest 2 decimals, and then we append it to the intervals, and then we can finally display the sample means and the intervals. Then later we calculate the Pearson correlation coefficient for age, experience and employee table. So as you can see over here, we have given a predefined like we have typed in here a data frame. So data frame is basically a set of dictionary in which we have the keys to be the features, and the values, they are generally lists which have the values of the column of the data, like column of the feature. And after that, here we are converting each of these columns for age and experience into a numpy array, and using those arrays we are plotting a graph over here, and then we will be finding the Pearson's correlation coefficient using this predefined function Pearson R. And after that, similarly we will be finding for Spearman's coefficient also over here using a predefined function Pearson R. And after that, we will be having Spearman coefficient over here, which is displayed. And finally over here we have calculate the covariance matrix for the employee table and analyze it. So for the employee table, as you can see over here, the covariance matrix is calculated using this predefined function covariance, and then we perform a hypothesis testing with z-test. So basically z-test, we have 2 hypotheses. One, it can be either right or wrong. So if the hypothesis is accepted, it's fine. Otherwise we have an alternate hypothesis, that is the exact alternate of like opposite of what the hypothesis was. So here we have 2 like hypotheses which are taken. The first one is, at 95% interval, can the bank manager be 95% confidence that his waiting time is less than 6 minutes. So over here, basically the problem says that the current system in a bank has tellers which serve customers in 9 to 10 minutes, but a new system is implemented by the bank manager which he claims can reduce the time to less than 6 minutes. So over here he has given the mean of the new system and like the waiting times, and using that over here we find the z-score over here. And after that, here for 95% we will be having a z-score of 1.96 for single tail test, and for 99% we have 2.57 for single tail test. So if z is than 1.96, that means it lies outside the bell curve, so it is rejected. And if it is greater than 2.57, then in that case at 99% also confidence interval it is not accepted. In that case at 99% also it gets rejected. So here in this case we have waiting time less than 6 minutes gets rejected at 95%, but at 99% confidence level it is accepted. So that's all for experiment number 5. Hope you like this video. If you did, do give it a like and do subscribe to my channel for more such interesting videos, and see you guys in the next video.